When it comes to Coulomb's law, there is more than just scenarios in which two charges are located next to one another or multiple charges are located in a straight line. Sometimes the charges are at angles to one another, so you may have one charge to your left and one charge above you. An example like this. In this scenario, we have a 3 microcoulomb charge, a 6 microcoulomb charge, and a 9 microcoulomb charge. We'll call them charges A, B, and C. We're given some dimensions, and we're asked to find the total net force acting on B and the total net force acting on A. Now, what we mean by net force here is A and B are obviously reacting. They're repelling one another, and B and C are also repelling one another. So if we look at B, it's both being repelled upwards by C, because it's going to be repelled away from C, and it's going to be repelled to the right from A. So really, B is going to be repelled up and to the right, so we want to figure out that combination of those forces, how is that actually going to cause charge B to move or accelerate. So the way we do that, there's a few different ways, but I'm going to show you my recommended method. We'll apply it to both find the net force on B as well as the net force on A. You could certainly apply it to find the net force on C, but I'll show you how to find these two as an example. So in general, I highly recommend you start off by finding the triangle geometry. And what I mean by that, if you look at our little diagram, if I overlay a triangle over that, what we really want to figure out is the side of the triangle that we don't know, in this case, the length of the hypotenuse, or also known as the distance between charge A and C. And we want to find those two angles that I kind of signified on the inside. We know that that angle by the 6 microcoulomb charge is a 90-degree angle because that forms a right triangle. So really we want to find those two missing angles and the length of that hypotenuse, or the distance between A and C. I don't always need all that information, but if I have it, there's nothing I can't find in a problem like this. So to start off, we can just use Pythagorean theorem to find the hypotenuse. So if I plug in 5 for A and 4 for B, and then I just solve that out, I should find that the distance between A and C is 6.4 centimeters. So now that I know the length is 6.4 centimeters, I can write that in, and then we can move on and try and find each of these angles. To find the angles, we would use SOHCAHTOA. So in this case, I have all three sides, so I can actually use any of the trig functions. I just happen to choose sine, so I know that the sine of theta, or the sine of an angle, is the relationship of its opposite over its hypotenuse. So in this case, relative to the angle I'm looking at, the opposite side is 4, and the hypotenuse is 6.4. So the sine of theta is the ratio of 4 to 6.4. You might have to think back to geometry or maybe earlier in the year. If you now want to find this angle, we have to take the inverse sine of that ratio on the other side. So in your calculator, if we take the inverse sine of 4 over 6.4, whatever that gives us in our calculator should be our angle, which in this specific problem comes out to about 38.7. If you're not getting 38.7, make sure your calculator is in degree mode, and then you should be fine. All right, so now we know that that's 38.7 using SOHCAHTOA. I'll jot that in, and we can apply the same process to find the other angle. We can certainly also just add 90 and 38.7 and then subtract from 180, since the three angles of a triangle have to be summed to 180. But just to show you here, I can also use SOHCAHTOA, so you have several different methods. Once again, I'll use sine. In this case, the opposite side is now the 5 centimeters relative to this angle, and the hypotenuse is still 6.4. So if I take the inverse sine of 5 over 6.4, I get about 51.4 degrees. So more or less, it should probably be 51.3 to get me to a total of 180, but with rounding, you get the idea. So at this point, I found hypotenuse. I've used SOHCAHTOA to find those two angles, so I found all the triangle geometry for this layout. So the next thing I'd recommend you do is draw the forces. And what I mean by that is we're going to draw the individual forces. So all of these are positive, so they're all going to repel one another. So if I just draw those forces, they're going to look like this. Force AC is going to be a repulsive force, so A will be forced up in this direction away from C, and the action-reaction force will be the force between A and C pushing C in this direction. So if you look here, AC is basically, or the force between A and C is repelling A up and away from C and repelling C down and away from A. Likewise, A and B are both positive, so they're going to repel one another. So the force between A and B will repel A to the right, and it will also repel B to the left. Finally, B and C will repel each other as well. They're both positive, so that force between them will repel B upwards and C downwards. So that's kind of the orientation that I use when I drew each of these. Because they're all repelling, I just show each of those repelling away from one another. It's important to note action-reaction, the force between A and C is going to be the same. So this value and whatever the value of this is going to be the same, the value for FBC will be the same, and the value for FAB will also be the same, just in opposite directions. Every action has an equal and opposite reaction. All right, so we have our geometry. We have the forces there. We know exactly what direction they're going in. So the next step is going to be to calculate those individual forces. Now we have 6 arrows, 6 different forces, but we actually only have to do 3 calculations because of that action-reaction pairing I was just talking about. So I'm just going to plug it all in at once using Coulomb's law. If I plug in the Coulomb's constant for K, and then I just make sure I'm very careful, and I use the 3 and the 6 microcoulomb charge when I'm calculating the force between A and B, and the 5 centimeters, which converts to 0.05 meters. When I square the distance in the bottom, that will get me 64.73. If you look through, you'll see all I did was swapped out the charges as well as whatever the distance between them is. So in the second one, I used 0.064 on the bottom because those two charges, A and C, are located 6.4 centimeters apart. And in the final one, obviously 4 centimeters, so 0.04. And then the charges up top, I just changed whether it was the 3 and the 6 microcoulombs, the 3 and the 9, or the 6 and the 9, depending on the pairing. So if you plug those in, you should get these values. So now I know exactly what direction these are pointing in, and I know what their values are. So I can kind of just write them up top. So you can kind of see there that even though I only calculated 3 values, I can write 6 values because I know that the force between A and C will be equal for both A and C, and so on and so forth. Now we're pretty much at the end of the problem. Depending what we're looking for, we have all the values and all the directions of these forces. So the final step, once you have this, is going to kind of be 2 steps. You're going to draw the free body diagram and find the F net X and F net Y equations, just like we did when we analyzed forces. And then after you have those values, you're going to use the F net X and the F net Y to set up a right triangle and solve the problem. So I'm going to first apply this process to find the net force on B. So I'll clean this up a little bit. So to find the net force on B, as I said, the first thing we're going to do is we're going to draw a free body diagram. Now, charge B is right here. You can see there's a force going up and a force going to the right. We're going to ignore gravity and that kind of stuff. We're only going to look at the electric force. So the free body diagram would actually look like this. You have the 164.73 Newton force going to the right. That's the repulsion from B. And we also have a 303.4 Newton force going up. That was the repulsive force from A. And the 303.4 is the repulsive force from C. So there's only 2 forces acting on charge B. The vertical one from the positive charge C below it, and the one to the right, which is from the positive charge located on the left. Once I have that, the F net X and the F net Y equation for this specific charge are very easy. There's only one charge that acts along the X plane, which is the 64.73, and there's only one charge that acts along the Y, which is the 303.4. So very easy F net X, F net Y equation here. Once you know the total net force in the X and the total net force in the Y, then you just make a right triangle. So I'm going to start with the X. I drew the 64.73. From where I ended that arrow, I don't pick my pencil back up. From where I ended that arrow, I then add the Y going upwards. So I get this kind of right angle arrangement. And in order to find the answer, the final answer, the net force on B, it's just going to be the hypotenuse of that triangle. Now I need a direction as well, because force is a vector. Now this is at an angle, so I can't really say left, right, up, down. I need to actually find that angle. So if I can find the hypotenuse of this triangle and that angle, I'm going to be able to answer this question. So now it's just like we did at the very beginning. To find the hypotenuse, I can use Pythagorean theorem. So my A and my B are going to be 303.4 and 64.73. So if I just kind of solve out the rest of that, I will find that the total net force acting on charge B is 310.23 newtons. And again, I simply found that by just plugging in the values A and B into Pythagorean theorem to find the hypotenuse. To find theta, much like I did before, I can use SOHCAHTOA. In this case, I do have the hypotenuse, actually, because I just found it. So I can use any function. Because I was given opposite and adjacent in the beginning, I just chose tangent. However, since you do have the hypotenuse, which is 310.23, you can certainly use any of them. But using tangent in my example, we know the opposite side relative to that angle is the 303.4. We know that the adjacent is 64.73. So in order to solve for theta, if I take the inverse tangent of that ratio, 303.4 over 64.73, that should give me my angle. So I round a little bit here, but you get about 78 degrees. So that means that charge B is going to feel a total force from these two charges of 310.23 newtons, and it's going to be directed at a 78 degree angle. If I want to figure out the charge on A, same process, a little bit trickier because it's not a 90 degree angle. But once again, I'm going to draw this free body diagram. So I have the one force at 64.73 pointing straight to the left. I'm simply just copying what I see here. So straight to the left is 64.73. Now up at an angle, I have a force of 59.26 newtons. Now the reason I knew this was 38.7 was alternate interior angles. That's a lie if you're in geometry. This is because of vertical angles. The inside angle here, these vertical angles are going to be the same. So if this is 38.7, this has to be 38.7. It's one of those geometric rules of intersecting lines. So I know what those forces are and I know what the angle is. So now I can set up my F net X and my F net Y. Now in this case, the 64.73 is going to the left, so I have to make that negative. Left along the x-axis is negative, so negative 64.73. I'm then going to subtract, because again, the 59.26 is also going in some way to the left. However, it is not directly on the x-axis. So to find that x component, I have to subtract 59.26 and then multiply that by the cosine of that angle. So generally cosine will get you the x, sine will get you the y, because in this case that angle is measuring or referenced off the x-axis. So I plug that in my calculator. I will find, again rounding a little bit, that the total force pushing to the left is 111 newtons. For the F net Y, I only have one force that in any way, shape, or form is going upwards. That is once again the 59.26. In this case, however, though, it's not directly on the y-axis, so I have to multiply that by the sine of 38.7. The reason why it's positive in the F net Y is because it's going upwards. Upwards in the y is positive. It was a negative for the x because both of those were going left. So if I plug in my calculator, I will find that the total vertical, or the y force, is 37.05 newtons acting in the upwards direction. At this point, it is no different than what we solved before. I'm going to set up my triangle. I'll first draw the 111 newton force going to the left, and then from there, I will draw the vertical upwards 37.05. And if I can find the hypotenuse of that triangle as well as the angle, I'll have the answer to this question. So once again, we could just use Pythagorean theorem that hypotenuse squared is equal to the other two sides squared and added together. So if I just kind of solve this, take the square of both sides and then plug that in my calculator, I should find that charge A experiences a total net force. That's a combination of the repulsion from B and C of 117.02 newtons. To find the direction, once again, we just need to use SOHCAHTOA. So once again, I use the tangent, but you can use any because you have all three sides. So the opposite over the adjacent in this case is 37.05 over 111. And in my calculator, if I take the inverse tangent of that ratio, I will find that the angle at which this total net force acts on A is 18.46 degrees. So the net force on A is 117.02 newtons at an 18.46 degree angle.